We now continue with the 2.9 notes with example 3. We're given a function f of x equals x squared minus 4, where the domain is restricted to x greater than or equal to 0. And we're told that this function is 1 to 1 on that restricted domain. And then we have several things we need to do. I just noticed in looking at this, there are two part B's. So I guess we have A, B, C, and D. Sorry about that. Hadn't noticed that before. A says to find f inverse of x. So let's start with that. Remember, there's a four-step process we can often use to find the inverse function. So for part A, the first step is to replace f of x with y. The second step is to interchange the roles of x and y. That is, replace y with x, replace x with y. So swap x and y. The third step is to solve the new equation for y. So let's write y squared, I'm going to put it on the left now, equals, and I'll add 4 to both sides, x plus 4. And then to solve for y itself, we need to, since we have a square, we need to take the square root of both sides. So what that would actually give us is something like y equals plus or minus the square root of x plus 4. Now, we have to choose whether we want the plus or the minus sign in front of the square root. And for that, what we do is use the fact that the roles of x and y should get interchanged, which means that if in the original function x is greater than or equal to 0, then in the inverse function y should be greater than or equal to 0. So if x is greater than or equal to 0, then our inverse function should have y greater than or equal to 0. Therefore, we take the positive sign, and our inverse function, and I'll use the inverse notation now, would be the positive square root of x plus 4. So that concludes part A, and now we have the inverse function for our given function f. Part B asks us to show that if we perform the function composition f composed with f inverse, we get a cancellation. Let's see that that is indeed the case. So we'll do f of f inverse of x. Starting from the inside, our f inverse from the previous step is the square root of x plus 4. We're going to plug that into f. And for f of x, it's x squared minus 4. So we're going to take whatever we plug in this case, square root of x plus 4. We're going to square it and subtract 4. When we square the square root, we get simply x plus 4. Then we subtract 4. And indeed we get x. So it is the case that f and f inverse cancel under function composition. And if we did the composition in the opposite order, we would see the same thing would happen. Notice you can even look at the functions, how they are written, to see that there's a reversal going on. For f, you're squaring x and then subtracting 4. For f inverse, you're first adding 4, then taking a square root. So the square root is the reversal of the square, and adding 4 is the reversal of subtracting 4. So we can also look at it from that point of view. Part C says to graph f and f inverse on the same set of axes. So for this, I'm going to make a couple of tables of solutions. First, for f of x equals x squared minus 4, where x is greater than or equal to 0, I'll make a little table of x's and y's here. I'm going to choose 4 points, and I have to choose my x's greater than or equal to 0 so that the function will be 1 to 1. So I'm going to choose 0, 1, 2, and 3. To get the y, I square the x and then I subtract 4. So 0 squared minus 4 is negative 4. 1 squared minus 4 is negative 3. 2 squared minus 4 is 4 minus 4, or 0. And 3 squared minus 4 is 9 minus 4. Whoops. Oh, excuse me. Just a moment. I'm sorry about that. Sometimes when I hit something, the wrong thing on my tablet, all sorts of strange things happen. Things scroll, and it's a kind of frustrating, and unfortunately I guess there's not much I can do about it. It happens from time to time, so I'm sorry about that. I think I have things back under control for now, at least. For the last one, it's 3 squared minus 4 is 9 minus 4, which is 5. I suppose it has something to do with my own clumsiness, so I like to blame my computer, but it's probably more my fault than anything else. Okay, let's plot these points. 0, negative 4, 1, negative 3, 2, 0, and 3, 5. Come on now, work for me. Okay. And still kind of not behaving very well. This is half of a parabola with vertex at 0, negative 4. Lost one of my points. There it is. I'm glad my time isn't about running out. I'd be really panicking here. Okay, so that's the graph. Well, it's still behaving funny. Let me pause this. All right, I think I got my graph back in order. We'll see how things go now. We now want to graph f inverse. So we just found that f inverse of x is the square root of x plus 4. So I'm going to make a table for this function as well. And I'm going to cheat. What I'm going to do is just take the x's and y's from the first table and reverse them. Now, technically, I'm not cheating. I'm just being efficient, because if this is indeed the inverse function, it should reverse the roles of x and y. Now, you can check this by actually substituting some of these values of x back into the inverse function. For example, if you substitute in negative 4, it's negative 4 plus 4 is 0, and the square root of 0 is 0. You can check all of these and verify that they are indeed solutions of the equation of the inverse function. But this is something that we can do to save ourselves a little bit of time in graphing the inverse. Just reverse the x's and y's from the original function. Notice, by the way, that for this function, we need to have x plus 4 greater than or equal to 0. And if we solve that for x, we get x greater than or equal to negative 4. X plus 4 has to be greater than or equal to 0 so that we avoid negative numbers under the square root. And you can see that that's exactly what happens with our table. We are choosing x's greater than or equal to negative 4. So that falls into place as well. Okay, let me attempt to plot points without causing my computer to go into spasms. So negative 4, 0, negative 4, 0, negative 3, 1, 0, 2, and 5, 3. And what we get, I hope this looks halfway decent. Okay, something like that. Not perfect, but good enough. That's the graph. By the way, if we think about our transformation rules, the graph of f is a parabola shifted 4 units down. It's a parabola shifted 4 units down. It's actually half of the parabola, though, because of the restricted domain. The inverse function is the square root function shifted 4 units to the left. So you could also graph these functions according to the transformation rules, which were, I believe, section 2.7. So that fits in to what we are seeing as well. So you see, it all fits together, at least it should, if you're doing things the right way. Part D says, state the domain and range of f and f inverse. Well, let's look at f. This is part D. The domain of f is given. It's x greater than or equal to 0. So that's bracket 0 to infinity. So that was given because the domain was chosen for the function to be 1 to 1. The range of f, r sub f, from the graph we can see that the smallest y value is -4, and then the y's go up to positive infinity when we look at the half parabola. So the range would be -4 to infinity. Well, it turns out that the domain of f is identical to the range of f inverse. If you look at the graph of f inverse, the range, the set of possible y values, is y greater than or equal to 0. That is bracket 0 to infinity. So what we can say about the x's for f is what we can say about the y's for f inverse. And the range of f is identical to the domain of f inverse. In fact, that's what we put right here, that the x's have to be greater than or equal to -4. So what we can say about the x's for f inverse is what we would say about the y's for f. So the domain of f becomes the range of f inverse. The range of f becomes the domain of f inverse. This is a consequence of the fact that the roles of x and y are being interchanged when we look at these two functions. Now I'm going to add one more feature to the graph. I'm going to put in a diagonal line passing through the origin. So I should have labeled these earlier. This is f. This is f inverse. This is the line y equals x. And notice when you put that diagonal line in, you see that there's a symmetry with the two graphs, the graph of f and the graph of f inverse. In fact, we would say that the graph of f inverse is the reflection of the graph of f about the line y equals x. That's a consequence of the fact that we're interchanging the roles of x and y. We're swapping x's and y's, and that causes points such as this point and this point to be reflected across that diagonal line. So every point on the graph of f gets reflected across that diagonal line, and then that gives us the graph of f inverse. That's a consequence of swapping the x's and y's for all of the points on the graph. At the bottom of the notes, you see that everything that I've mentioned in this example is summarized in that final paragraph. For all one-to-one functions f, the domain of f is identical to the range of f inverse, and the range of f is identical to the domain of f inverse. Furthermore, the graph of f inverse is the reflection of the graph of f about the line with the equation y equals x. The identity function, this is the identity function f of x equals x actually. This is a consequence of the fact that for any point AB on the graph of f, the point BA is on the graph of f inverse, where the roles of x and y have been interchanged. I am nearly out of time. Thank you, and see you at the next lesson.